What's going on, guys? In this video, we're going to be covering 3 different ensemble methods of bagging, random forest, and boosting. So let's first start off with what is an ensemble method. So with an ensemble method, you're going to combine the results from a bunch of weak learners. And the idea is that by combining a bunch of results from these weak learners, we're going to get better accuracy. So they're often paired with decision trees because you can easily control the complexity of decision trees to make them weak learners by simply limiting the number of leaves. So the first ensemble method we're going to talk about is bagging. So with bagging, we're going to create a bunch of bootstrap samples and then form decision trees from each of these bootstrap samples. And the idea is that by having slightly different data and building a bunch of trees and average them together, we're going to be able to greatly decrease the variance, which is one of the biggest problems with decision trees. So the first step, let's form our first bootstrap sample. So remember, with bootstrap samples, we're going to simply randomly pick observations for our original data set, and observations can be chosen more than once. So let's say we choose observation 1, we'll have observation 2, and then let's say observation 3 gets chosen twice. And finally, we'll choose observation 5. So notice that observation 4 didn't get included. So this becomes grouped into what is known as our out-of-bag samples. So for out-of-bag, we're going to have a y value equal to 10, an x1 value equal to 4, and an x2 value equal to 15. And then after we create our first bootstrap sample, we can make a decision tree from our data. So you would do this just like you would a regular decision tree, but with our new data. So you'd find whichever split creates the lowest sum of squared error. So let's say the split that we chose is going to be x1 is less than or equal to 4. So doing this, we'd have observations 1, 2, 3, and 4 from our new data set on the left, which would have y values 2, 4, 8, and 8. And then on the right, we would just have our last observation with a y value of 12. So then you would take the mean of these observations, so your predicted value would be 5.5, and your predicted value would be 12. So that's going to be our first bag decision tree. And now we can repeat this process to form our second one. So let's say observation 1 gets chosen. And let's say observation 1 gets chosen again. And then we'll say that observation 2 gets skipped, and then the next 3 observations get chosen. So then observation 2 gets grouped into what's known as the out-of-bag samples. So it has a y value of 4, and an x1 value of 2, and an x2 value of 8. And then, just like before, we're going to form a decision tree of our new data. So let's say this time the best split is x2 is less than 4. So this would put the first 2 observations on the left, so we'd have y values 2 and 2, and the next 3 observations on the right, so 8, 10, and 12. So when we average our results, we get 2 and 10. And then essentially you would repeat this process hundreds, if not thousands of times. Now, the number of trees is not a tuning parameter, but essentially you don't want to stop until your out-of-bag mean squared error or error rate stops increasing or decreasing. And then we're going to learn how to solve for the out-of-bag error rate. And when we're creating our trees, essentially you're usually going to end up with large trees, and you're not going to use any pruning, but for demonstration purposes, we're only going to use one split here. So after we create our chain of trees, here are only 2, you can make predictions from them. So in order to make a prediction, say we had an x1 value equal to 3 and an x2 value equal to 5. So in order to make a prediction, we would simply plug it into our trees. So from our first tree, we have the rule that if x1 is less than or equal to 4, we would guess a predicted value of 5.5. So from our first tree, our predicted value would be 5.5. Then we'd run these same samples in our next tree. So in our next tree, it's saying if x2 is less than 4, we would guess 2. If not, we would guess 10. So here we would guess 10. And then you simply divide by the number of trees we created. So our estimated prediction for an x1 value of 3 and x2 value of 2 would be 7.75, would be our predicted value. So now we can talk about our out-of-bag samples. So our out-of-bag samples can be used to estimate our test error. So instead of using cross-validation, you can use your out-of-bag samples. Now generally for your out-of-bag samples, about 1/3 of your total observations are going to fall in these out-of-bag samples. Since we only did a really short data set here, we only had one sample, but generally it's going to be 1/3 of all your observations. So in order to find your out-of-bag mean squared error, for this case, and if it's classification, it would be accuracy, but since it's a regression problem, it will be mean squared error, we would simply plug in our out-of-bag sample into their respective decision trees, and then find their total sum of squares, and then in the end, we'll just divide by n. So, for instance, for our first out-of-bag sample, we had a y value of 10, and x1 value equal to 4, and x2 value equal to 15. So when we plug that into the respective decision tree, which is x1 is less than or equal to 4, we would guess 5.5. So here we would guess 5.5, and our observed value was 10. So our residual is going to be 10 minus 5.5 squared. And then we do the same thing for our next out-of-bag samples, which here we see we have a y value of 4, an x1 of 2, and x2 of 8. So we plug that into the respective decision tree, which is if x2 is less than 4, we'll guess 2. If not, we'll guess 10. So since x2 is greater than 4, we would guess 10. So our observed value is 4, minus our predicted value, which is 10, squared. So our sum of squared error total is going to be equal to 10 minus 5.5 squared plus 4 minus 10 squared. And then in order to find our estimated test mean squared error, we simply divide these results, or sum of squared error, over n, which is just the number of out-of-bag samples, which is 2. And by doing this, we can get our mean squared error value equal to 28.125 for our out-of-bag samples. So when we create a long series of decision trees instead of just one decision tree, we're going to lose a lot of interpretability of our model, because we're no longer going to say that when x1 is less than 5, we get blank. But we can still get a measure of the variable importance, or the amount that our predictor decides in deciding our dependent variable. So for regression, we would say that our variable importance is equal to the total sum of squared error decrease caused by our predictor, whichever predictor it is. So let's say if x2, every time a split was based on x2, and we summed up all the results of these splits for the decrease in the sum of squared error, the total of that would be equal to our variable importance. So the more that this predictor causes a decrease in the sum of squared error over all our decision trees, the higher the variable importance. And then for classification, we can say the same thing, except we would say that the increase that our predictor causes in purity. So for each split over all our decision trees from our bag samples, whichever predictor causes the biggest increase in purity, we would say has the most variable importance. So the major problem with bagging is that if you have an extremely important predictor, ultimately it's going to decide most of the splits. So let's say x1 was an extremely important predictor. And let's say each of our trees started with, say, x1 is less than 3.5, x1 is less than 3.6, x1 is less than 3.4. And let's say you had 30 predictors. And this is how all your decision trees started. Ultimately, this would create a bunch of decision trees which are pretty much exactly the same, which defeats the purpose of creating a bunch of bag decision trees, because ultimately you want different trees in the hopes of lowering the variance. If you end up with a bunch of the same trees, ultimately you're saying that you have a bunch of correlated trees, which defeats the purpose of using bagging. So in order to address this, we can use random forest. So random forest works the exact same way as Bayesian. So we're going to create our bootstrap sample, and then we're going to create our decision tree off this bootstrap sample, and then we'll create another bootstrap sample, decision tree, so on, so on, so on, hundreds of times, if not thousands, just like we would for Bayesian. And then when we analyze our results, we would go about the exact same way, where we would plug in our observations to each of our decision trees, and then either average our results for regression, or we would take the mode of our results for classification. But the difference when we are going to use random forest is that each of the splits, we can only consider a subset of the possible predictors. So let's say here that we had 16 predictors in our data. So for our first split, we might say we can only use predictors 1, 5, 8, and 12. And then we would choose whichever one of these predictors created the best split, just like we would any decision tree. But we're only considering these 4 out of 16. And then when we go to our next split, we might say we can only consider predictors 8, 9, 15, and 16. So at each split, we're only going to choose, say, 4 of the possible 16 predictors. So these number of predictors that we're choosing at each split is a tuning parameter. So this P, or the number of predictors chosen, or I think the book uses M or M trie. For classification, this number is going to generally be around the square root of P. So here we had 16 predictors, so it would be around the square root of 16, which is equal to 4. But it's a tuning parameter just like any other model. You would use cross-validation and say try different values such as 2, 3, 4, 5. And then for regression, the total number of predictors is going to generally be around 1 over 3 times the number of predictors. So we had 16, so it would just be 16 over 3, so it would be about 5. So the idea is that by limiting the number of predictors we can choose for each of our splits, we're ultimately going to end up with a bunch of different decision trees, because if you have one extremely important predictor, say predictor 2 was the most important in the model, it won't be able to dominate the splits, because essentially it won't be included in each of the possible splits that you can do. So the idea is that by limiting the number of variables in each of our splits, we can greater decrease the variance compared to Bayesian, and we won't end up with correlated decision trees. So now we can talk about boosting. So boosting works in a completely different manner than with Bayesian and random forest. Whereas with Bayesian and random forest, we formed a bunch of bootstrap samples and then formed individual decision trees on each of these bootstrap samples. Boosting instead is going to form a decision tree based on the results of the past decision tree. So you shouldn't have to be able to solve for a boosting problem on the exam, but for clarity, I'm going to do a short example. So in order to initialize our boosted model, the first step is we're going to guess our predicted value as the mean of our dependent variable. So here if we take the mean of 20, 40, 60, 80, we would just get 50. So that's the first step to initialize our model. Now that we initialize our model, we can form our first decision tree. So in order to form our decision trees, we're going to use our residuals is now going to take the place of our output, or dependent variable. So to form our residuals, we guessed a predicted value of 50 for all our observations. So the first residual, we had observed 20, predicted value of 50, so our residual is going to be negative 30. Then for the next one, negative 10, 10, and 30. So now we would form a decision tree just like we would any other way, based off now our R is going to take our Y value, and we're still going to use X1 as our independent variable. So let's say our first split we want to do if X1 is less than 4. So if we do this, observations 1 and 2 will fall on the left, so this would be residual values of negative 30 and negative 10. And then on the right we had observations 3 and 4, so this would just be 10 and 30. So just like any other decision tree, we just take the mean of each of our sides, so negative 20 and 20 would be our predicted values. So now we can find our predicted values after one iteration. So after one iteration, we would say we started with 50, and now we're going to add, and we're going to talk about lambda, which is going to be our learning rate. Here we're just going to set it equal to 0.1. and then times our results after our first tree. So for our first two observations, we guessed a value of -20. This is observation 1. So after one iteration, our predicted value is going to be 48 for observation 1. Then for observation 2, again, we started with a predicted value of 50, and then we added -20 times our learning rate, so our predicted value will be 48. And then for observation 3, since our predicted value is now going to be 20, we're just going to use that instead of -20, so our predicted value will be 52. And then for observation 4, our predicted value will be the same as for observation 3, so we get a predicted value equal to 52. So now if we add this to our data, so our predicted value for our first two was 48, and for our second two was 52. So these are going to be our predicted values if we only had one iteration of boosting. So now we can find our residuals if we want to use another iteration. So our y value is 20, we predicted 48. So our residual is -28. For the next observation, our y value is 40, we guessed 48, so -8. And then 8 and 28. So the major thing to look at. So when we first initialized our model, our residual is -30. After one iteration, it's now -28. And then looking at observation 2, we went from -10 to -8, then 10 to 8, 30 to 28. So notice that all our residual values after each iteration will tend to shrink towards 0. So this is a good thing because ultimately we're going to lessen and lessen our residuals after each iteration. So now we can do the same thing for our second iteration. So we're going to build another decision tree. So we'll just use x1 is less than a 4 again, although it doesn't have to be the same rule each time. So this would put observations 1 and 2 on the left, so we would use the residual values, so -28, -8. On the right, we would use 8 and 28. Then we would find the mean of these values, so -18 and 18. So if we want to find the predicted value of our observations after 2 iterations, we'll just use observation 1 and observation 4. So for observation 1, we started as our first predicted value was 50. And then our next predicted value was -20 we found. And then finally, after 2 trees, our predicted value was -18. So our predicted value after 2 trees for observation 1 would be 46.2. And then if we wanted the same thing for observation 4, we started at 50, and then we added our learning rate times -20, and then plus our learning rate, and our predicted value was 18. So our predicted value for observation 4 after 2 iterations would be 53.8. So our residual after 2 iterations, we had an observed value of 20, we guessed a value of 46.2. So our residual will be -26.2. And then for our other observation 4, our predicted value is 53.8, observed value 80. So our residual is just 26.2. So again, notice after another iteration, our residuals decreased in size towards 0. So now we can talk about the tuning parameters of our boosted model. So first we had lambda, which is going to be our learning rate. So as we increase our value of lambda, it's going to lead to our bias to decrease, but variance to increase. So this is because as we increase lambda, we will approach 0 faster and faster, so we can expect lower bias. But an effect of this is that we're going to have increased variance. So the second tuning parameter that we're going to have is B, or the number of trees. So notice that in bagging, number of trees wasn't a tuning parameter, because essentially you can't overfit a model by adding more and more trees to bagging or random forest. But with boosting, by adding more trees, you're controlling the complexity of your model. So for number of trees, as we increase our value of B, our bias will decrease and variance will increase. So this is because at each iteration we expect to get closer and closer to 0, which is another way of saying we're going to eventually overfit our model, as our bias is going to decrease more and more and more. And then our last one is going to be D, which is just going to be the number of leaves. So unlike in bagging or random forest, we're going to have a set number of leaves for each of our decision trees. So it's generally going to be a smaller tree, and as we increase this number, our bias will decrease and our variance will increase. Which makes sense because generally if you expect, say, a smaller tree, let's say only one split, we'd expect this to be very low variance but high bias. And then if we create deeper trees, we would expect lower bias but higher variance. So as we increase the number of leaves, we're going to have lower bias but higher variance. So now we can talk about the differences between them. So with bagging and random forest, it's essentially the same model. The only difference is that with random forest, we're only going to consider a subset of the predictors at each of the splits. And the reason for doing this is that so we don't end up with correlated trees, so it can ultimately lower the variance better. Now with boosting, it's very different from the other two, where each tree is going to be grown sequentially where each tree is going to depend on the last tree. Generally, you're going to use smaller trees, and we're going to have 3 tuning parameters, with one of them being the number of trees. Now, with bagging in random forests, each tree is going to be grown independently, so one tree is not going to depend on the last tree. We're going to use larger trees. And then for random forest, the only tuning parameter we're going to have is going to be M, or the number of predictors we can consider at each split. So the number of trees is not going to be a tuning parameter when we're using bagging in random forests. So that will wrap up this video. If you want to see a better example, a more extensive one on boosting, so you shouldn't have to know how to solve these problems, but if it'll help you to understand better, StatQuest has really good videos on it. It's like a 4-part series. And other than that, I'll see you guys next time for unsupervised learning. Thanks.